Welcome to the third video in our reflection series where we look at the SimpleCPU and reflect upon how it went and what could be improved. This week we're looking at the SimpleCPU version 1D. To overcome the limitations of the SimpleCPU version 1A, there's some significant changes to the architecture of the SimpleCPU version 1D, as we can see here. If you look at its new block diagram, you can see we've moved away from the accumulator to a register file, and with some additional inputs to our address and data multiplexers to allow us to implement different addressing modes. So to understand how we got to this point, we need to go back and look at the SimpleCPU version 1A for a moment. Okay, so the SimpleCPU version 1A was an accumulator-based architecture, and the ALU could process 8-bit values. However, the external memory was 16 bits wide, and that was to do with the size of the instruction. So to keep the fetch phase simple, all instructions are fixed length, all instructions are 16 bits long and stored in one memory location. They can't be spread over multiple memory locations. The choice to have different data sizes and instruction sizes was deliberate, because what I wanted to highlight was that the size of your instruction is to some extent linked to your data size, but it's a loose coupling in that the size of a machine level instruction is determined by its opcode field and the number of operands that are used in that instruction. So obviously some of those will be absolute addressing mode instructions, will be the size of your address bus, and some of those operands will be immediate values, which will be or could be linked to the size of your data registers inside your processor, but not necessarily. So there is a separation, and we see that in modern machines. So you can have 64-bit data registers, but a 32-bit instruction format, as we see in some of the MIPS machines. Therefore, having this difference raises some questions about how do we influence some of our machine-level instructions, such as the load and store instruction. So, for example, our store instruction, where we want to store the accumulator value out to memory, the address operand obviously is an 8-bit value because we have a 8-bit address bus. But our data value stored in the accumulator is also 8 bits, and it's been written to a 16-bit storage location out in memory. So we've got a decision, how do we handle that difference? And also the other way around, when we're executing a load instruction, we'll be reading a 16-bit value from memory and wanting to store it obviously to an 8-bit accumulator, and obviously it won't fit. So this mismatch in sizes gives us some design choices. Obviously, ideally, we'd go to byte addressable memory, where the processor could individually address each byte in memory, but that comes at a cost. That adds complexity to our memory architecture. As you can see here in this block diagram, so now that we need to be able to read and write to each byte separately, one way of doing that is to separate our memories out into two blocks. So we'd have a high byte and a low byte memory. As a result of that, we actually half the addressable range. So previously we had 256 16-bit addressable locations. Now we will only have 128 16-bit locations, but we still can address 256 things, but now we're addressing 256 bytes rather than 256 words, 16-bit locations. As you can see from this block diagram, we didn't want to compromise performance, so these two memories are operated in parallel, so to allow us to read the low and high byte at the same time when we do an instruction fetch, because we want to read a 16-bit value when we read the instruction. But when we want to read a particular byte, we're using the high 7 bits of the address bus to address these memories, and the least significant bit of the address bus bit 0, to either enable a specific memory block when we do a store instruction, or to control the additional multiplex you can see here in this block diagram to select either the high byte or the low byte, depending on what address we're reading. So if it's an even address, we'll read the low byte, and if it's an odd address, we'll read the high byte. So in some respects, this gives us the best memory architecture. We're using every single byte, we're not wasting anything, but we have effectively halved our memory size. So our maximum program size is now limited to 128 machine-level instructions, rather than in the previous case we had 256. So it is a design decision. Do we want more instructions, or do we want to have more efficiency in how we save our data? And as I said, for the SimpleCPU, I kept it simple, because the typical programming examples we use for the SimpleCPU 1A don't have that many data values, so it's not too much of an inconvenience wasting that memory each time we store a variable in memory. So that gets us back to the SimpleCPU version 1D we can see here. So to simplify the load and the store operations, the internal data registers are now 16 bits. So when we do a read and a write, there's no problem. External memory 16 bits, internal data register 16 bits. So the load and store instructions can just transfer that data without any issues owing to them being different sizes. Also, to improve performance, we've moved to a register file. So we have 4 general purpose registers, RA, B, C, and D, giving the programmer a little bit more flexibility in where they store their variables. And we've also increased the size of external memory. We increased it from 256 addressable locations up to 4096, so 4K's worth of storage. And obviously all these changes have had an impact on the instruction formats, as you can see here. But again, I've stuck to a 16-bit fixed length instruction format, exactly the same as the SimpleCPU version 1A, so this machine can run exactly the same programs, but I have added some additional addressing modes. Now, moving to a 16-bit data register within the processor does come with some complexities. Obviously, if your instructions are 16 bits and your data registers are 16 bits, there's no space for the opcode. So you can't define a 16-bit immediate value directly within the instruction. And that's not uncommon. You'll see that in other processors' instruction sets. So what we do here, you can see in the top example, we have some examples of immediate addressing mode instructions. So again, we stick with a 4-bit opcode. Now we have a 2-bit register select field, because now we have to select between our 4 general purpose data registers. Previously it was implicit, data always came from and went to the accumulator. Now we have a choice, so that's what that 2-bit field does. We have 2 bits unused, and then we have an 8-bit immediate value. I could have used the 2 not used bits to extend this bit field to a 10-bit immediate value, but I decided to keep it to 8 bits. Now, as this 8-bit immediate value is going into a 16-bit general purpose register, obviously that needs to be sign extend, and that's what that RTL description down the bottom there is showing you. So when you move that 8-bit value into a 16-bit register, the sign bit is used to sign extend it up to that 16-bit space. Having a register file obviously allows us to have some different addressing modes. So in the middle there you see an example of a register addressing mode. So in this example we have a move instruction, so we can move values between registers now. And obviously you have 2 register select fields now, one for the source and one for the destination. As these register addressing mode instructions don't have numbers in them, they don't need the lower 8 bits to represent an address or an immediate value. Those are free, unused. So we can use these bits to expand our opcode field. So when the top opcode is all ones, that indicates a register addressing mode instruction, and the particular type of register addressing mode instruction is defined by the lower 4-bit opcode field. Finally, obviously we expanded the addressable space up to 4K, so we now need 12 bits of address for our absolute instruction. And you may not be surprised, that's what the 4 unused bits were in the original SimpleCPU version 1A's instruction set. So if you go back and look at those instructions, you'll see there was 4 unused bits, and they are now being used to hold the 4 extra bits that we need for our 12-bit address. Another improvement made to the SimpleCPU version 1D was to add subroutines to add the call and return instructions to our processor. So we can define a function once, a subroutine, and then call that functionality from different points in our program. So we don't have to cut and paste the same code throughout the program. Which means we improve our code density. We make the most of that 4K memory block. Now, to implement these call and return instructions, obviously we need a call and return stack. We need somewhere to save that return address. Classically, that's done using a stack stored in external memory. However, that does add significant hardware complexities. A much easier way of implementing the call and return stack is using a hardware LIFO, a last in first out buffer, a stack stored in the program counter. And it's exactly what the PicoBlaze processor does do. So I based the call and return stack for the SimpleCPU version 1D on that idea. So this schematic here, it shows you now the program counter for the SimpleCPU. So the top half of it implements program counter, exactly the same building blocks as that used in the SimpleCPU version 1A, but in the lower half there you can see we have a LIFO buffer, a LIFO 12 component, and each time a subroutine is called, the return address is pushed onto that stack. So if you push into that LIFO buffer, you'll see this schematic. So to keep things simple, I've limited the number of nested subroutines to 4. So you can have a subroutine that calls a subroutine that calls a subroutine, calls a subroutine that calls a subroutine. And if you try and have any more nesting, obviously we run out of memory, because if you look inside this component, you'll see that there are 4 12-bit registers, to store 4 return addresses, and if you go any deeper than that, you run out of space. And the same is true for the Pico Blaze processor. I think it could support 16 nested subroutine calls, and for small applications obviously that's fine, because you're not typically using recursive programming. For those sorts of applications, that level of nesting is perfectly fine. One final change to the SimpleCPU version 1D was how you define the control logic. So in the previous designs, the control logic was implemented as a schematic. However, I wanted to introduce in this module some level of hardware description languages, HDLs, as those are typically what are used out in industry now. So for the control logic of the SimpleCPU version 1D, it's implemented in VHDL. And I've limited the style of VHDL just to combinatorial logic. So we're not looking at any register definitions here in the VHDL. We're purely describing Boolean logic, which I think is quite intuitive. As coincidentally, it uses a similar format as the RTL descriptions that the students have been used to define their machine level instructions. So for more information on the SimpleCPU version 1D, do refer to this webpage. It takes you through the design of this processor. As I say, fundamentally it's very similar to the SimpleCPU version 1A, just with some extra features. One thing I forgot to highlight in the previous discussions was obviously going to a 16-bit general purpose register means that all the data paths and number crunching units within the ALU need to be increased from 8 bits to 16 bits to support that. So that obviously comes at a significant hardware cost, basically doubling the size of everything. And you can see that here. This is the new and improved ALU for the new processor. Again, it contains our basic processing elements. So we've got an adder subtractor unit, a bitwise and this time we've also got a rotate hardware block, which implements a bit shift just using wires, buffers to perform that shift operation. We also have some unused inputs in this ALU. So you can see the lower multiplexer has 4 constants connected to its inputs. And the intention here is that this processor will be used in the assessment. So the students can replace those constant components with additional hardware elements when they implement their own machine level instructions, and hopefully can replace a series of simple machine level instructions with a more complex machine level instruction. So for example, if you were doing multiplication, you could replace the shift and add instructions that are typically used in a software implementation with a hardware multiplier. And obviously you'd get the associated increase in performance, because obviously now you could do a multiplication in a single instruction. Okay, so to wrap this video up, so reflecting on the SimpleCPU version 1D, it all worked nicely in the lab, and this is the process I'm currently using to build the games console. So in addition to this processor, I developed a simple VGA controller, so we've got some graphics. The user input can be sourced from either a rotary encoder or a Super NES games controller. It has a nice simple input, or a PS2 keyboard. And using these peripheral devices, I've implemented Space Invaders, Pong, Noughts and Crosses, and Conway's Game of Life. So even with this simple instruction set and this limited memory, you can still do basic games quite easily. So some things are kind of a little bit painful with this instruction set are the limitations placed upon you by the immediate addressing mode, only being allowed to define an 8-bit signed value. So you're limited to plus 127 to minus 128 as a data value, which has its positives and negatives. It's a pain, but I think it also highlights to the students that design decisions always are a compromise. Yes, we would like to define larger values, larger immediate values, but that would mean going to a variable length instruction format, and that obviously has costs associated with the fetch phase that makes it more complex. So there's always advantages and disadvantages with every decision made. The grass is always greener when you look at someone else's instruction set. Again, another limitation of this machine was that it only had 4 general purpose registers, which is definitely a plus compared to the original machine. But again, 4 general purpose registers is a little bit limiting. Another thing that could be improved is obviously the call and return structure. So without direct support for an external stack, that is your pop and push instructions, passing parameters to subroutines has to be done either via registers or external memory locations. So it becomes a little bit more complex for the programmer, as they have to remember what registers are being used and what external memory locations have been used. Whereas if you've got a stack and you're pushing parameters onto the stack, that's automatically done for you by the stack frame. So it's a lot more tidier, it's a lot more efficient in that sense. So as you can probably guess, that's where we're heading now with the SimpleCPU version 1E. We will be again improving our processor, adding additional capabilities. Okay, I think that's where I'll leave it now, and I'll see you next week.